First, I want to give you a big picture about this project. Why do we want coercion quantification and what's going on here? The long-term goal of our project is to have dependent Haskell. Suppose this whole big box is what you want from the Haskell, and now we want it to be dependently typed. And the first step towards dependent Haskell is to have a dependent core. And during the meta-theory study of dependent core, we found that we want homogeneous equality. And while implementing homogeneous equality, we found that we want coercion quantification. So this little corner in this whole this big picture is all this talk is about. If you are not familiar with some of the concepts, no worries, I will explain them in details later. So in this talk, I will first tell you the story from Haskell to coercion quantification. And when we have the background knowledge, we can dive into the coercion quantification a little bit more. So the theory and the implementation under coercion quantification might be interesting for co-contributors. And we also prepare an open question in the design space in source Haskell for Haskell users. And finally, we will discuss some of the future work. So let's get started with the story. We said that the long-term goal of our project is dependent Haskell. So the first question that comes into mind is, why do we want dependent types? When we say a language has dependent types, we mean that there could be some references to types inside, to programs inside types. For example, for vectors, we can encode the length of the vector in the type signature of vector. Here, we define this natural number, which is either a 0 or a suc of another natural number. And in the type signature of vector, we expect a value of length net, which is the length of the vector. For example, the data constructor nil is a vector of length 0, and the cons accept a value of type A and a vector of length n and returns you a vector of suc n. For example, a vector of 1, 2, 3 is a vector of length 3. You cannot claim that it has length 2. You will get a type error. Once we have the length indexed vector, we are ready to define some well-behaved functions. For example, the head of the vector, in this vec_hand, we always return the head of a vector, but we can only have a non-empty vector to return the head. So in the type signature of this vec_hand, we say that we expect a vector of length which is greater than 0. Now, if you apply this vec_hand to a nil, you will get a type error instead of some runtime exceptions. And we can use type families in Haskell to define the addition in the type level. Once we have the addition, we can define the function append, which says, give me a vector of length n and a vector of length m. I will return you a vector of n plus m. So as you can see, dependent types helps us eliminate the errors like the head of a nil or like the wrong definition of append. And it also can enable us to write type level computations. And what I haven't shown in the example is sometimes we also use dependent types to carry equivalence proofs and so on. But even if you are convinced by me that dependent types are useful, why do we want dependent Haskell? Given the fact that we are already being able to write the data type vector and the function vec_head and append. Well, yes, there are lots of extensions we provide inside GHC to provide the ability to program as if we had dependent types. And we work so hard for each extension to make sure it behaves well and they interact with each other perfectly. But this also means we need to study each meta theory for each extension independently. There is no unified meta theory of the extensions. And also, it will sometimes cause duplications in the code. For example, we use type family to define the type level plus for natural number, but sometimes we also want the term level plus for natural numbers. Now we have two definitions of natural numbers with two definitions of plus with exactly the same functionality, but we want both of them because they behave in different levels. And what worse, even if we work so hard on these extensions, we still have many restrictions on those kind of extensions. For example, restrictions on type family and data family. So our plan is to extend GHC with full spectral data types. And it would be compatible with the current implementation, but it will largely simplify and unify lots of GHC's extensions. The first step towards dependent Haskell is to have dependent core. If we want to add dependent types to GHC in one patch, well, that would be very difficult. So this is the high-level dependency graph between modules in GHC. Well, compatibility with existing features in GHC makes adding full-fledged dependent types very difficult. But luckily, GHC incorporates several compilation phases, so it is possible to change one of the intermediate languages without affecting the user experience at all. So the language we choose is the dependent core as a step towards dependent Haskell, which is well studied in this ICFP paper. And you can find some discussions about the implementation of dependent Haskell in this Haskell wiki, Dependent Haskell Phase 2. But during the meta-theory study of dependent core, we found that we want homogeneous equality. What is homogeneous equality? Given an equality proposition, two terms A and B with type capital A and B, in homogeneous equality, this A and B would be definitionally equivalent types. But in heterogeneous equality, A and B may be unrelated. I quote from this ICFP paper. So the most important change is we show that the homogeneous equality is compatible with implicit coercion proofs, and it simplifies both the language semantics and the proofs. So we want homogeneous equality, but what do the other stuff have to do with coercion quantification? Well, suppose we have homogeneous equality in GHC, which is written like A is total hash with B in core. And how can we define this can-indexed GADT? Here, we want to define this data type. And the interesting point about this data type is there are two data constructors, and they instantiate the canned variable k with different canned. In the first data constructor, rep Boolean, it instantiates k to type. And in the second one, it instantiates k to type. So how can we represent this data constructor in core? We might want to do something like this. So here we say that given me the constraint that k is equivalent to type and a is equivalent to Boolean, I want to return rep ka. But however, this definition is ill-candid because we say that this total hash expects two types on both sides are of the same kind. And here, A is of kind k and Boolean is of kind type. So what do we need to do here? Well, we want to give an explicit name for the coercion. Here, we use this CV to represent the kind coercion. And then we use this coercion to cast the kind of A from k to type. And similarly, in the rep maybe, we cast it from k to type. Now we have well-defined types for this rep Boolean and rep maybe. Well, for presentation purpose, the code in source Haskell will be black, and the code in core would be in blue. Given the background knowledge, like why do we want coercion quantification, now we can dive into coercion quantification a little bit more. What is coercion quantification? Coercion quantification is the quantification over a coercion variable, and there are two places such kind of coercion can appear. The first one we have already seen is a for all type over coercion variable. Here, in the type of rep Boolean, the second for all quantifies over a coercion variable. And this coercion variable represents a canned coercion, which is used later to do the cast. Because in GHC, we can lift the for all type, we can lift types to coercions. So we also need a for all coercion over coercion variable. Here, this for all C, C1, C2 is a coercion which coerces from a for all type over coercion variable into another for all type over coercion variable. The first contribution of this project is we studied the meta theory of the coercion quantification, including like typing rules and how it interacts with other coercions and the optimization and so on. So for example, the typing rule for all coercion over coercion variable looks like this. I'm not going to explain the rule for you. I put the rule here just to scare you. The second contribution of our project is we implemented coercion quantification inside GHC. You can find our code in this patch, the 5054. After our patch, now both for all type and for all core can quantify over coercion variables, but only in core, not in source Haskell. And we have updated all relevant functions accordingly. To give you a taste about what has been changed in core, let's take this data count as an example. So if now if you define a data constructor in source Haskell, it would be represented as a data count in core. So it has the universal type variable, which is a list of type variable, and existential type variable, and we also record the user written type variable binders. So now we previously we have the invariant that the set of type variable in user written type variable is equivalent to the set of universal type variable union with existential type variable. But now we are allowing coercion variable to appear as existential variables. So we rename this existential type variable to existential type coercion variables, and we have a new invariant saying that the type variables in user written type variable binder is equivalent to universal type variable binder union with type variables in existential type coercion variable. There are many similar changes like this in core, but no worries, we have updated all the notes and comments to match exactly what have been changed. But as a Haskell user, you may wonder, if all those changes just happen in core, why do I need to care about coercion quantification at all? Well, since the core now becomes more expressive, we do have a new open question in the design space in source Haskell. For example, do you think the compiler should accept the type of fun? Here, I define this data type same kind, which expects two type arguments of the same kind as its name suggests. And we give this, we define this type signature for this function fun. So in the type signature, the type variable A expects a kind K1, and the type variable B is of kind K2. And now I say, give me a constraint that K1 is equivalent to K2. I want to return this same kind A and B. Well, do you think the compiler should accept this program? Well, we want it to, but now it is rejected. Because A and B are of different kinds. But if we have coercion quantification, and the compiler, the solver is not smart enough, it should be able to generate a name for you for this kind coercion, and then insert the cast for the type variable A to cast its kind from K1 to K2 and to accept this program. But this means it will need non-trivial extensions to the solver, and we are not sure whether this feature is ever desired during Haskell users' development. Future work of this project includes to implement the homogeneous equality in core, and then we can start to really implement dependent core, and finally lift the dependent types into source Haskell. The reference includes two PhD dissertation and this ICFP paper about dependent Haskell's in dependent types in Haskell. Here, we want to especially thank Google Summer of Code to support this project and also the broader community from Summer of Haskell, without whom this project would be impossible. And that's all about this talk. I'm happy to take any question.
Thank you, great stuff. Where are all the questions? So I'm very confused. I've read the System SC papers, probably all of them, and you always could scope over coercions. There was also always a lambda with a coercion in there. So can you explain how this word different? So what's really added to System SE? I'm just missing it. I believe it's there, but if you could explain it to me, please.
You read the paper System FC?
Yeah, there were always lambdas with coercions as far as I know, or weren't there?
I'm not sure.
Somebody can enlighten me. Okay. Right. Sorry, what was the answer?
Yeah.
The new thing is called the lambda coercion, so the time coercion.
So it's what it's scoped over. All right. Do we have any more questions? No, you go ahead.
Mine isn't very important. It's very conventional, but there's one thing I took from the recent work on the time here is that there's a middle ground between heterogeneous properties and homogeneous properties. The equality parameterized by another equality quantified. And since in court, since that the general form is A coercion coercion is equal to B, maybe it should be called equality in court might make sense. And so just, yeah, it's very tangential, and I don't know if you thought about this. I don't know.
I've thought about it a little bit, but I want to talk further to see exactly what new expressiveness that would either enable or disable, sort of depending on what you're comparing it to. Because there's a lot of different ways of phrasing equality, but I think a lot of them are more sort of equivalent, and just some maybe has more syntactic noise or something than another.
So the interesting compared to the ideal making the students line heterogeneous in service handle is that this just like having a hidden parameter on that. So there's something cute there. I don't know if it's worth it.
We could talk further. My instinct is that this is equivalent in expressiveness to homogeneous equality, but maybe there's some subtlety to it.
Okay, good question. Okay, so you said that you gave an example of like in source Haskell where a need for this could potentially come up, but mentioned that it's unclear if anyone like actually wants to do that particular thing, and that you may not want to make that example actually possible in source Haskell. Is the coercion quantification that you just that you implemented though, is it fundamentally important for things that dependent Haskell is going to be able to do? And if so, are you able to describe like a very simple example of like where that comes up in dependent Haskell?
So the motivation for coercion quantification is to implement homogeneous equality, which is important for the meta theory of dependent Haskell.
Okay.
Well, if we can also have dependent Haskell with heterogeneous equality, let's say, but we will lose some meta theory about it.
Okay.
And the coercion quantification is about implementation in GHC, like to prepare for dependent Haskell.
Okay.
Okay, I guess one last question.
So
that were the reason, then you could have used the Congress closure procedure that Lean is using for intentional type theory with heterogeneous quality. To do that. I don't know if that would sidestep all of this if you already have imaginary stories.
I don't know the theory you mentioned, so yeah, maybe we can investigate it more later.
Right. Then I'd like to thank you again.
Thank you.